So naturally, any discussion of weak acids in this chapter 9 extend themselves to buffers, because buffers are really just a mixture of the weak acid and a little bit of its conjugate base. So if you've got both HA and A minus in solution, if you have both of those, you've got a buffer. If you've only got a tiny bit of one or the other, then maybe you don't have a great buffer, or maybe you have an asymmetric buffer, but you still have a buffer. That is the simplest definition. Its purpose, what do buffers do, I think we all have a general idea, but the reminder here is that it resists change in pH whenever you add some concentrated acids or bases. So we're all made of buffers, right? That's the only reason we're alive. Otherwise, if you drank some orange juice for breakfast, you would die immediately, because the pH change would not be resisted from the liquid in your body or the water in your body. And so instantly you'd go from a blood pH of roughly 7.4 to a pH of 2.5 or 3, and your cells would no longer function. And so buffers are enormously important. The entire ocean is a buffer. One of the most important buffers, really probably the most important buffer, is our ocean, because it buffers the CO2 from the atmosphere. In which case we're getting into trouble because we have lots of CO2 being generated from anthropogenic sources like our cars in our industry. And so as we generate more and more CO2, what we're doing is essentially pushing the equilibrium of the buffer in the system to make more acidic pHs. We're making more carbonic acid by dissolving more CO2, which means that things like calcium carbonate, which constitute our corals, those things start to dissolve because their equilibrium gets pushed away from solubility, and so those things get more and more soluble in water because we have more acid in solution, which is why we have ocean acidification. That's how all those things are connected, right? And it all comes back to this notion of buffers. And so we've got to talk about buffers because buffers are the key to understanding titrations, which are where we're going to go after this. So if you've got a buffer, which is what I've got drawn up here, it's just a beaker, and you've got a buffered solution. So you've got some HA and some A minus. The cool thing about buffers is if you add a little bit of H plus to the solution, what that's going to do is combine with the A minus, and it's going to shift the equilibrium back towards HA. If you add a little bit of base, we'll just write base like that, that's going to react with the HA, and it's going to shift the equilibrium a little bit back there. And so it's the ratio of those two things, HA and A minus, that give us a little bit of wiggle room, where we don't get major swings in pH because we have both of those to sort of balance out any additions from H plus or base. Of course, that's all within reason, because if we add enough H plus or base or hydroxide to this to destroy either one of those, then our buffer is done. Then we've completely destroyed that half of the buffer, and then we get to a point in a titration or in your human body where the system is no longer responsive or resistant to changes in pH, and we get wild, massive sort of asymptotic swings in the pH. And so if we want to think about like the difference between a buffered and a non-buffered solution, if you have a non-buffered beaker here and you start adding a little bit of H plus, maybe in the form of HCl, which is what we have on the x-axis here, what we'd see is pretty much an immediate, instantaneous decrease in the pH. Simply because all of the HCl that gets added is in the form of H+. And so now, because pH is simply the negative log of that value, we get a very, very rapid decrease in pH as the increase of H+ is essentially linear. What happens to a buffered system, the picture to the left? Well, it doesn't mean we don't get any change in pH. It just means that that pH is much slower to change until we run out of buffer. And then we start to see that asymptotic change. And so this is the benefit of the buffer, like the oceans or our human bodies or virtually any living organism. So we got to think about the formalisms of buffers because they're invaluable to how we live. Okay, so no good conversation about buffers goes without talking about Henderson Hasselbach. I don't love the fact that they get an equation named after them. I'm a little bit sore about that because really, as you'll see, these guys were doctors. They were medical doctors, and all they did was a log transform of the existing equilibrium concentration or equilibrium expression, and they got their names on it, and we use this all the time, but really it's the existing equilibrium expression that was around much longer than they were. This came around about 100 years ago. They wrote this up in a medical journal, and they were the first to publish it, which is why they got their name associated with it, but they were certainly not the first ones to consider it. And so it's a little bit annoying because it wasn't really a discovery. It was literally what you'll see here, being very quick. So we start with just the general reaction scheme for a weak acid, which is HA proceeds to dissociate to H plus and A minus. That's our starting point, and we know that the extent of that equilibrium is governed by its Ka. So we can craft the equilibrium expression for that, which is simply just the products over the reactants is equal to that equilibrium constant. So next thing we're going to do is just take the log of both sides of these parts of the expression. So that looks something like this. So I've highlighted Henderson and Hasselbach's contribution here in green, just in case you were unaware. Next thing we do is just distribute this log or decompose this log term using log rules. That looks something like that. So you've still got log Ka on the left side of the expression, and then I'm just extracting the H plus and using this addition. So we know that if you have a log of two terms multiplied by each other, then distributing the log allows us to add them. So now I've got log H plus log, and now I still have that same ratio, A minus over HA. I'm going to do a little switcheroo with this expression. So I'm going to take all the term on the left, the log K, I'm going to bring it to the right, and I'm going to take all the terms on the right, I'm going to bring it left. So it's going to invert the signs in front of each of those terms. That gives us something that looks like this, and now we're getting to the space where we start to recognize some stuff. So if you didn't already see this coming, what's minus log of H? Well, that's pH. And what's minus log of Ka? Well, that's pKa. So I'm going to take this last term here and I'm going to bring it over to this side, and then we'll see the final form of our what we call the Henderson-Hasselbach equation. So there's the expression. I'll call it the Henderson-Hasselbach just because it doesn't have another name and I don't want to confuse you. I just want you to know that simply taking the log of both sides was all those folks did to get their name on this thing, because it's literally the same expression that you would have started with for a weak acid dissolving in water, but they just took the log of both sides. What's the utility of this thing? Well, it's nice because we're often working in terms of pH and pKa, and it also sort of simplifies our ability to understand small changes in concentrations of A minus and HA and how those impact the pH. So let's think a little bit about the implications. All right, so first sort of thought experiment here is what happens when HA, which is the acid, the weak acid, is equal to A minus in the solution. What happens to our expression? Well, if those two things are equal, then this becomes log of 1, which is 0, and so we end up having pKa plus 0, which means that the pH is equal to the pKa. That's a critical part. So when you have a weak acid and its conjugate base in solution, and you tune those or you adjust those such that they're equal to each other in solution, either by adding acid or base, at that point the pH of the solution is equal to whatever the pKa of that weak acid is. That's a crucial point, or of course this is like a central point of our titration curves that we're going to talk about in a little bit when we compute those. The other utility here is just how simple it is to think about different changes in ratios of A minus to HA. So again, if we're thinking about HA proceeds to make H plus plus A minus, and we think about really this as a sort of balancing act, right? The equilibrium is telling us whether it lies to the left or left to the right. If we push the equilibrium in our buffer such that there's a lot more A minus than there is HA, and maybe we hypothesize that that this ratio is actually like 10 to 1. There's about 10 times as much A minus as there is HA in solution, so it's heavily product favored in that case. You've added a lot of base. What does that mean for the pH of the solution? Well, that just becomes a log of 10, which is 1, so pH is just equal to pKa plus 1. And the same is true, but opposite, if the equilibrium is lying heavily to the left by say, a factor of 10. And so if we add a bunch of acid and we've got roughly 10 times the amount of acid compared with base, then log of 0.1 or 1 over 10 is -1, and we end up with pH equal to pKa minus 1. So how can we generalize this? Well, for every factor of 10 change in the ratio of the conjugate base to the acid, we get 1 unit in pH change. The direction of that change depends on whether you're above 1 or below 1, whether you have more acid or more base. But that's the utility in framing it with this Henderson Hasselbach formalism, because it's really easy to understand simple changes in the ratios of the acid and the base. Okay, so the last concept that I want to convey, just staring at this Henderson-Hasselbach equation, is how do you make the best buffer? And by best buffer, I mean, how do you make a buffer that's going to be good and be responsive to additions in either direction, meaning either adding acid or base to the system? If you look at this, we should be able to draw that conclusion pretty generally, right? So think about that for a second. Think about at what pH would we want to construct a buffer, and why, to give us the most symmetric response in both the acid addition direction and the base addition direction. So hopefully, and certainly if you took a course with me, I talked a lot about this, but you probably heard about this from whoever taught you Gen Chem, but also hopefully also in organic chemistry. You're always going to want to construct your buffer, at least if you're trying to construct it symmetrically, which almost all buffers are constructed symmetrically. In that case, you're going to want an equal amount of both A minus and HA in the system, right? You want equal amounts of these. You don't want a ton of one and a little bit of the other. Because if you've got everything in the HA form and you have almost 0 A minus, that means when you go to add H plus to the system, there's almost nothing there, which means it's not going to be buffered from the acid direction. It's going to be well buffered from the hydroxide direction, because if I add hydroxide, there's an abundance of HA to sweep up that and neutralize that OH. So at what point do we have equal amounts? Well, that comes down to our first situation here, right? When the pH is equal to the pKa, that means that those two species are equivalent to each other, where HA and A minus are equal, and that's the aim. So if you you're in a biochemistry course, or you're in my research lab, and we're trying to do something, and we say, okay, we want to make a buffer, and we want that buffer to be at 6.2. How do you know what species to even choose? Well, that's when you go to a pKa table and you look up, and it'll give you a pKa, and it'll just list it from small to large, and it'll 0.1 all the way up to 6.2 and up to 11.4. It'll be this huge table, and then it will tell you the chemistry, exactly what the acid and conjugate base pair are that you would need to construct for this. Or in other words, it would give you the acid that has a pKa associated with that. And so you would look and you would say, okay, what's the closest thing? Maybe 6.2 isn't on the list, but maybe 6.3 is the closest thing to what you're shooting for. In that case, you would look up at whatever that chemistry is, and you'd say, that's the thing I need to choose to make my buffer with, because if I choose that and I set the pH equal to the pKa of that particular species, then I'm going to have almost equal amounts of both the base and the acid in solution, which is your goal if you want a really good buffer, symmetric buffer, to buffer in both directions.